Hello friends, today we are going to start new third unit of digital communication, that is random signal and noise. But before starting with this unit, let's have a quick revision what we have studied up till now. Now starting with unit number 1, that is digital transmission of analog signals. In that we have studied basics of digital communication. Why digital communication? What is sampling? What is the significance of sampling? We have seen different modulation techniques, then pulse code modulation, delta modulation, adaptive delta modulation. After that, we move to the second unit, that is baseband digital transmission. In that we came to know if many sources are there, want to transmit the information simultaneously, then over there we use multiplexing. We have studied what are the types of multiplexing, hierarchies, digital multiplexers. After that, we have seen that how digital data is converted into digital signal, that is line codes. Then we have seen what are the characteristic properties of line codes, types of line codes as like your unipolar, polar, bipolar. Then we got the knowledge of intersymbol interferences, scramblers, equalizers. So here it is your third unit, that is random signal and noise. In this we have to study the mathematical definition of random process, stationary process, various statistical properties like mean, correlation, covariance, what are ergodic process, power spectral density, noise, Gaussian process. For this unit, we are going to refer a book, Digital Communication System by Simon Hagen. Now, in the design of digital communication, it is very important to mathematically analyze the sources that are going to generate information. After that, transmission channel it is there, and last, design of receiver it is there. So what are the objectives of this third unit? So students are expected to be able to understand what are random variables, what are random process, understand types of random process, what is power spectral density, and what is Gaussian process and noise, and then mathematical analysis of random process, CDF, your PDF, power spectral density, etc. The outcomes of this unit, after completion of this unit, students will be able to understand that what is a random process, what is mean, correlation, covariance. These all are the statistical properties of random processes. Then they would understand the types of random processes, that is stationary, non-stationary process, wide sense stationary process, ergodic process. Then they would understand what is power spectral density, Gaussian process and noise. Today we are going to cover random variables, random process, what is ensemble, and the mathematical representation of it. Many times the messages that need to be transmitted are random in nature. Basically, signal are of two types, deterministic and non-deterministic. A signal is said to be deterministic if there is no uncertainty with respect to its value at any instant of time, or signals which can be defined exactly by mathematical formula. A signal is said to be non-deterministic if there is uncertainty with respect to its value at any instant of time. It means we couldn't know the precise value of the signal in advance. Non-deterministic signals are random in nature and hence they are called what? Random signals. For example, consider a radio communication system. The received signal in such system usually it consists of what? First, information bearing signal. After that, it has a random interferences component, and last, the receiver noise. Now, the information bearing signal component may represent your television signals, your computer data, or voice signals. So suppose it is a voice signal. So basically voice signal it consists of what? Randomly spaced burst of energies of random duration. And the second one, that is the interference component, may produce the electromagnetic disturbance or waveform by the communication system which is working in the vicinity of the radio receiver. A major source of receiver noise is your thermal noise, so which is caused by the random motion of the electrons in conductors and devices at the front end of the receiver. Although it is not possible to predict the precise value of a random signal in advance, so it may be described in terms of its statistical properties such as your mean, average power, power spectral distribution. The mathematical discipline that deals with such statistical characterization of random signal is called as what? Probability theory. So probability theory is rooted in a phenomena that can be modeled by an experiment with an outcome that is subject to chance. Moreover, if we are going to repeat this experiment for a number of times, the outcome can differ because of the influence of what? Random phenomena or chance mechanism. Such experiment is called as what? Random experiment. For example, throwing a dice or tossing a coin. These are the examples of random experiments because we don't know that what would be the value in advance. To be more precise, the random experiment it has following three features. First is the experiment should be it is repeatable under identical condition. On any trial of the experiment, the outcome should be or it is unpredictable in nature. And third, for large number of trials of the experiment, the outcome exhibit statistical regularity. That is, it is going to provide some definite average pattern. So before starting our actual unit random process, it is necessary to understand what is random variable. So let's move on to see what is random variable. Let a random experiment having sample space capital S and elements small s belongs to sample space capital S. Then we can define a function x of s whose domain is S and whose range is set of numbers on real line. So we can consider an experiment of tossing of a coin. So hence in tossing of a coin the possible outcomes are what? Head and tail. So sample space, it would be, there are two possibilities, head and tail. So let we define function x of s such that x of s is equal to 1 when s is equal to h, that is head, and it would be -1 if outcome is what? Tail. So we have drawn a sample space S over here, that is capital S, and this is your real line. So it will be -infinity to +infinity. Now suppose that S1, there are two possible outcomes are there. So that's why suppose it is S1, it is there. Sample point. Another sample point, it could be what? Tail. So we represent it as S2. So the mapping of this sample points on a real line. So x of S1, it belongs to what? +1 on this real line. Whereas S2, that is tail, it is -1. It belongs to or mapping onto this real line, that is -1. So the two possible outcomes are mapped onto this 2 points, that is +-1 on real line. So we can define random variable as a function whose domain is sample space. Whose domain is what? Sample space, and whose range is some set of real numbers is called what? Random variable. So let us consider a event k which denote one of the possible outcomes of a random experiment, and it represents what? Head. So what is the probability? The probability, it would be what? It is head represented by h upon sample space. Sample space over here, it is what? 2. So it is 1 upon 2. It means 50% probability it is of head, it could come. Similarly, if we are talking about a tail, then probability of coming outcome tail, it is what? T upon sample space. Over here also sample space, it is what? 2, and then it would become 1 upon 2. So over here the probability of outcome, it is defined. Why? Because sample space is over here, it is a defined. But if sample space is undefined, it means it is has a very large number. So we can tell it tends to what? Infinity. So what would be the case? The first case, it could be that probability is equal to k upon sample space. So we have considered sample space over here it is infinity. So anything upon infinity is what? 0. So since the probability it is coming what? 0, so it is not a random variable. Similarly, the case is second, that what if the outcome or the events are equal to sample space, that is it would be k upon k. Then what would be the probability? Is a 1, because outcome is equal to sample space. So if it is so, we couldn't tell that it is a random. There is no random variation it is there. So that's why it is also not a random variable. So we can say that random variable, it is lying between what? 0 and 1. Now, random variable, it is of two types: continuous random variable and discrete random variable. Now, since it is a discrete random variable, so we can plot a graph, that is a probability versus the range. Since it is a discrete, it means the outcome, it present at a what? Particular instant. Suppose at instant 1 it is output, it is there. At instant 2 output, it is there. At instant 3 it is there. So it means in between 1 to 2 the outcome, it is not there. It is a discrete, it is not a continuous. The outcome, it is present at what? A particular instant of this range. So it is called what? A discrete random variable. Like this one. But what about a continuous random variable? Continuous random variable, it means, suppose it is like this one. So there is a possibility, it means continuous random variable, it means what? That it is not present at a just a fixed interval 1, 2, 3, 4, 5. It is also present in between 1 to 2, 2 to 3, 3 to 4 and 4 to 5. So it is a continuous. That's why I have drawn like this one. So understood that what is discrete random variable and what is continuous random variable. Now moving towards our actual topic, that is random process. So basically the concept of a random process, it is an extension of random variable. So a random variable which is a function of time is nothing but your random process. So it is denoted by x of t. So any random variable which is depends on the time, whose value depends on the time, it is called what? Random process. So x of t, it is going to denote a random variable for every instant of time. Or we can say random variable, it is what? Indexed by t. So t over here it is what? Indexing set. Now consider a random variable x which represents what? The temperature of a city at 12 o'clock. So we are going to consider over here example. Now the temperature x is nothing but a random variable and it can take on different values on different day, right? Now in order to get the complete idea about this random variable x, we will have to do the record values of x at 12 o'clock over many days. So we can here define that suppose one sample point, it is of S1. Next, it is of temperature at a 12 o'clock on day 1. So it is temperature at 12 o'clock on day 1. Similarly, we have to record the values for many days. So suppose on second day also we have recorded, it is S2. Similarly, S3, S4, S5, S6 and so on. So after doing so, the sample space, this is a sample space of this random variable. It would look like this. Each sample point over here, it is going to correspond to the what? Temperature at 12 o'clock on their respective day, on that particular day. Getting? So S1 corresponds to temperature at 12 o'clock day 1. S2 corresponds to temperature at 12 o'clock on day 2, day 3, day 4, day 5, day 6, and so on. But the temperature is not just the function of a day. Exactly. Because the temperature, it also depends on the time. Morning it would be temperature, it would be different. In the afternoon it would be high, and in the evening again it is going to decrease. So temperature is not just a function of a day, but it is also a function of time. So that means the temperature at 1 p.m. will have a completely different distribution from the distribution of temperature at 12 o'clock. So since the temperature, it is a function of time, so suppose at 12 o'clock we have defined the sample space, but for at 1 o'clock we have to again record the values. For that we have to draw a different sample space. So we can define another random variable to represent the city temperature at 1 o'clock. So this sample space has sample points like S1 dash. So it is going to represent the temperature of a city at 1 p.m. 1 o'clock on day 1. So again we have to record the temperature for day 2. So it would be represented by S2 dash. Similarly S3 dash, S4 dash, S5 dash, and so on. Now moving towards the sample function. Now what we have to do it, the next step it would be there that after recording the city temperature for each value like 12 o'clock, 1 o'clock, similarly we have to draw the sample space at a 2 o'clock, 3 o'clock on every day. And we have to then plot the waveform. So that waveform, it could be represented by what? X of lambda t. This lambda it indicates what? Day. So lambda 1 it would be represented what? Day 1. Lambda 2 it is going to represent day 2, and so on. Now see this figure. Basically this is a graph of temperature with respect to the time. So this graph, it is nothing but the temperature variation with respect to the time on day 1. So it is going to represent it by x of lambda 1 comma t, or we can represent it as of capital X of t comma lambda 1. It represents same. What is lambda 1 over here? Lambda 1 it is going to represent what? Day 1. So we have to record the value on day 1, the temperature of a city on day 1. It is like this one. So this waveform is called as what? Sample function, and this is nothing but your sample function 1. Because earlier what I told, that sample function, it is a waveform showing the variation with respect to what? time. So since it is of day 1, it is called a sample function 1. So this is the instant time, that is t1, small t1, at which we are going to record the temperature. Similarly, we are going to record the temperature at instant small t2. Capital T1, it is going to represent you what? Temperature. Temperature 1. It means on day 1. Similarly, observe the second waveform. It is T2 of small t1. T1, it is the instant, it means the same timing for particular day at which we are going to record the temperature. Say it is a small t1. Similarly, we are going to record the value of a temperature on day 2 at instant t2. So this is a graph. It is going to show you what temperature on day 2 represented by x of t comma lambda 2. Lambda 2, it is nothing but what? Your day 2. This is called a sample function 2. Now similarly, we have to go on day 3. So it is a temperature on day 3 represented by x of t comma lambda 3. So it is T3 of T1 at instant T1. We have recorded the temperature. Then this is at instant, sorry, it is 2. We have recorded the temperature on day 3. And similarly, we have to record the temperature for n number of day. So basically this figure, it is nothing but your ensemble of sample function. Now what is ensemble? Ensemble, it means a family or a collection. So collection of all the possible sample function is called what? Ensemble. So the collection of all the sample functions, it is nothing but what? Ensemble. Remember. Now sample space is the collection of what? All possible sample points. But whereas ensemble, it is a collection of all possible sample function, and this is a similarity between your sample space and ensemble. So remember that x1, it is nothing but x of t1. So over here x1, it is what? A random variable which is generated by the amplitude of this random process at instant t1. And similarly x2, it is also another random variable which is generated by the amplitude of random process at instant t2. So hope you got the relationship between random variable and random process. Remember guys, this is a random process, but at a particular instant, if I am going to take the reading, say it is a t1, it would become a random variable. So as you know that mapping of sample points on a real line, it is what? Random variable. But the mapping of sample points on this waveform is called what? Random process. So just discussing a few concepts, that sample space is nothing but your collection of all possible sample points, whereas ensemble, it is the collection of all possible sample function. We can also say that ensemble comprised of functions of time, it is also called as random process. Each sample function, it consists of infinite sample points. So ensemble of sample functions will consist of, also it would consist of what? Infinite sample points. Since a group of sample points, say S1, S2, S3 and S1, it corresponds to what? One random variable that we have seen that at 12 o'clock we are going to define the sample points S1, S2, S3 up to S1. So they are going to correspond to what? One random variable. Then we have seen S1 dash, S2 dash, S3 dash for second random variable. So the ensemble of all these random variable, it would correspond to what? Infinite number of random variable. So we can also say that random process is what? Collection of infinite number of random variable. And this random process, it is also called as what? Stochastic process. It means whose value it could not be predicted. We have to guess it. So that is called what? Stochastic process. Now moving towards a few differences between random variable and random process. So we can say random variable, the process by which mapping of each sample point on real line, it is what? Random variable. It may not be function of time, but random process, the process by which mapping of each sample point to a waveform on a waveform, it is called random process. And remember, sample process is always function of time. One more, that random variable, it may not be function of time and only ensemble averages it can be calculated. And random variable could be continuous random variable or it could be discrete random variable. And random variable, it is just a set of numbers. But what about random process? Random process, basically it is of two types. It could be stationary process, it could be ergodic process, that we would see later on in next lecture. And in random process, the ensemble as well as time averages, both it could be calculated. And random process, it is not just a set of numbers, it is a waveform. So hope you got the difference between random process and random variable. See guys, I am giving a much time to this topic random process so that afterwards you can understand the topics easily. Now, moving towards a mathematical representation of random process, as we know that random process, it is nothing but a random variable which is function of time. So that's why we have written capital X of in bracket lambda comma t. Why t? Because this random variable, since it is a function of time, it become what? Random process. So we can define that it equal to x of lambda 1 comma t, as we have seen on this waveform, that is lambda 1, lambda 2 or lambda n, it is going to represent what? Different random variables, and this is your time instant c. So in mathematical form we can define that random process is equal to x of lambda 1 comma t, x of lambda 2 comma t, lambda 3 comma t, and so on up to n variable. So this is nothing but what? Your sample function, what we have seen in the waveform. So each one, it is going to represent you what? Sample function. So random process, it is nothing but a collection of your sample function. Since over here it is a t, it is here time it is a continuous. So this random process, it is also called as what? Continuous time random process, because what we are going to do it, we are going to mapping sample points on continuous time varying function. Or in another way, how we can define the random process? Now we have defined the random process in terms of what? Collection of sample functions. Now in terms of random variable, if I am want to write the random process in terms of random variable, then how we can write it? Over here, x of lambda t is equal to what? X of lambda t1 at instant t1. Similarly, x of lambda comma t2, t3, it means at a particular instant. Lambda, it is, suppose example what we have taken over temperature. So you have to measure the temperature at T1, T2, T3 and so on. But lambda over here, it is going to represent you the day. Okay. Number of this on day we are going to represent at T1, at T2, at T3 and so on Tn. So this is nothing but your random variable. So this is random variable. Why it is random variable? I already told you, because we are going to measure the temperature at a particular instant of time. In I'm taken the example that it is a temperature. So at a particular instant of time we are going to measure it. That's why it is called a random variable. So the collection of random variables, it is also a what? Random process. But now over here, instead of t, if it is n, it is there, then it means it is a discrete time random process, it is there. Then the t, it is going to be replaced by what? Small n. So for a discrete time random process, the random process, it could be defined as x of lambda comma n is equal to x of lambda 1 comma n comma x of lambda 2 n, x of lambda 3 n and so on. So each this one, it is going to tell you sample function 1, sample function 2, 3 and up to n sample function. So the collection of these sample function, it is called what? Discrete time random process. It is one and same, just t, it is replaced by n. In terms of random variable, we can define x of lambda n is equal to x of lambda n1. That it means a particular instant we are going to measure it. So it is at n2, n3, n4 or nth of n value. So each is going to represent you what? Random variable. So random variable 1, 2, 3 up to nth random variable. So the collection of these random variable, it is nothing but what? Your random process. So it is in continuous time and this is on your discrete time. So it is going to map discrete time random process. It is going to map a sample points on discrete time varying function, and over here it is a continuous time varying function. So it is all about the mathematical representation of your random process. Now moving towards the end of this lecture, if you really understood this one, now you have to tell me, suppose let x of lambda t, it is your continuous time random process, then what x of lambda 1 t it is going to represent, that you have to tell. Again, what is x of lambda t1, what it is going to represent, and what is x of lambda 2 comma t1 it is going to represent. So you have to tell me, if you really understood this one, you have to tell me that what is it. Since first it is x of lambda 1 t, it means we are going to measure for the time, that is over the interval, over the time, since it is called as what? Sample function. And the second one, it is what? At a particular instant we are going to measure it. So what I told, if at a particular instant of random process, if you are going to measure, then it would become what? Random variable. And what about this x of lambda 2 comma t1? It means this is the value, this is the value lambda 2 which is taken by this random variable, that is t1. at instant t1. So value taken by random variable. Now similarly, if it is a discrete time random process, it is there, then x of lambda 1 comma n, what is going to represent? Just t, it is going to replaced by what? It is n. So similarly, it is called as what? A particular function, that is sample function. What about this x of lambda comma n1 at a particular instant n1 we are going to measure, so it would become what? Random variable. And what about the next? It means it has taken the value at a particular instant n1, so it is a value taken by random variable. So today we have studied random process. So in today's lecture, we have seen that what is random variable, what is a random process. Then with the help of waveform, we came to know about that what is sample function, what is ensemble, what are the differences between random variable and random process, and how to represent mathematically random process. This is the assignment. Please note down this assignment, as you have to solve this assignment and submit to us. In next lecture, we are going to see the types of random processes. We are going to discuss stationary processes, the types of it, then ergodic process, what are the statistical properties like mean, correlation and covariance. So for any questions and feedback, this is the email address. So it's about today's lecture. Thank you very much.